Good morning, ladies and gentlemen. I'm Sujay King Liu, and I'll have the pleasure of chairing this next session, Session 6, on memory devices. So the first speaker is Professor Philip Wang from Stanford University. His talk is entitled, Emerging Memories, Are They Energy Efficient Enough? Professor Wang joined Stanford University as a professor of electrical engineering in 2004 after a distinguished career at IBM T.J. Watson Research Center. At IBM, he held various positions and had the responsibility of shaping and executing IBM's strategy in nanoscience, nanoscale science and technology, as well as exploratory silicon devices and semiconductor technology. His current research at Stanford covers a broad range of topics, including carbon nanotubes, biosensors, self-assembly, exploratory logic devices, nanoelectromechanical relays, device modeling, and novel memory devices, such as the ones that he'll talk about today. He received his PhD from Lehigh University, and he currently holds the Chair of Excellence of the French Nanosciences Foundation. Please join me in welcoming Professor Wang.
Thank you. All right, good morning. Oh, thank you. Morning? Oh, okay, good. Thank you. So we heard a lot about switches for the last day and a half, day and this morning, and I'd like to switch gears a little bit and talk about memory. Okay, since we are in this E3S symposium, so I want to focus this discussion on memory on understanding whether they are, what the energy dissipation of this energy and the energy systems, right? So, okay. So why I want to talk about memory. So if you look at this simple collection of pictures that you see in the screen in here, and think about what kind of new gadgets that we all have in our pockets, in our home, and so on and so forth, that you quickly realize that many of these new gadgets or new embedded system, you can call it that way, if you think of it that way, that are really enabled by memory. Okay, you can think of, but a lot of people would thought that, well, the digital camera is really enabled by the ubiquitous image sensor, but really, if you do not have the card that holds the data, the humongous amount of data or megapixels of data that you have, the digital camera is not going to be very successful. So memory has been, and I assert that it will be and continue to be a key enabler for new applications. That's from the embedded system point of view, and let's take a look at the processor. And you've probably seen this picture many, many times, in which you quickly recognize that even though there are a number of cores, which we all talk about for the past day or so, about 50% roughly of the chip is occupied by either the memory controller or the memory itself, which shows up as various levels of cache in terms of SRAM. So from a chip area point of view, you have a lot of the memory as well. And if you think about a bigger picture, well, the chip goes into a processor, and processor goes into a server, and server goes into a data center, and things of that sort. Then these are some numbers that I noticed from a paper from David Miller back in 2009. Where it says that the CPU itself consumes about 30 to 60% of the server power, and about 50% of the CPU power is consumed in devices, and which, by the way, exceeds the total amount of power generated from solar back in 2007. So a lot of the power, a good fraction of the power consumed in devices, and some of these devices are logic switches, and some of them are memory. All right, let's drill down to the processor. Let's say a processor, and looking at what is the relative role of the memory and the logic switches. So here, Amdahl's law, well, it's not law, rule, says that the megabytes to the MIPS ratio used to be, when he proposed the rule, it used to be about 1. Today is about 4, is rising. So the amount of memory that you required on a balanced processor system versus the processing power measured in terms of MIPS has been increasing. Okay, and the other thing that I wanted to note is that this is a paper from Shaker-Boker from Intel. It shows the non-cache transistors versus number of years. This is the cache transistors in megabytes versus years. you can see that the slopes for these cache transistors rises a lot faster than the non-cache transistors for two reasons. Number one, the non-cache memory transistors are increasing slowly because of power constraint. That's the only you can only afford so much of these, so many of these devices that are running at blinding speed. And the other one is really the need for more and more access to memory. So, and the prediction is that memory integration capacity will quickly outpace logic by about 10x very soon. And another way to look into this is to look at this paper from Intel, again, 2010, showing a Intel 48-core processor in 45 nanometer CMOS. This pie chart says the core occupied uses about 70% of the power for this high performance mode, and then this little pie, this substantial pie, is for the memory controller and the DRAM, DDR controllers. And here you have low power mode, and more and more of the fraction is occupied by the memory. Okay. So the punchline for this is that even though we talk about computation, logic switches, and communications, which we'll talk about this afternoon, transporting information from one to another, which is these two pies in here, we really should not forget about the memory for building a processor system or building any electronic system. Okay. So what are the opportunities here? So shown in here is the bandwidth in megabytes per second. This is a chart from Jim Handy from Hot Chips last year. This is price per gigabyte. The hard disk drive and the tape are getting cheaper and cheaper. As we all know, you can go to Best Buy and buy cheaper and cheaper disks every year for higher capacity, but they're not getting any faster. So they are moving in that direction. They're cheaper but not faster. At the same time, all these DRAM and SRAMs on chip is becoming a little bit faster and also cheaper, so they're moving in this direction. So here you can see the result is that the gap is widening, it's opening up between the solid state storage on chip and the hard disk drive and the tapes that are off chip. Okay, so that's opportunity there. So the opportunities for memories are that the white space have really opened up in this memory hierarchy, the storage hierarchy of the speed versus capacity. There's a gap in there. And the other direction is that from an applications point of view, from the point of view of building embedded systems, building processor systems, you need lots of gigabytes or terabytes. So for various applications. And so you need high-density memory technology. The question then is, will these memories be energy efficient enough? Okay, so that's what we want to answer. So there are a lot of emerging memory that has been proposed and explored in the technical community. Today I want to just focus on 4 of them: phase change memory, various acronyms for it, spin torque transfer, STT-RAM, resistor switching, metal oxide memory, short RRAM, conductive bridge memory. You'll get another talk after this on CB-RAM and other applications and that. And then there are many others that fall into the category that I really can't make a good logic switch out of it, but it has some hysteresis, so let's call it a memory. So I'm not going to talk about those. Okay. All right, phase change memory, and the physical principle is very similar. It's very simple. You have a material, various kinds of materials, and we heard some superlattice phase change material yesterday, which is quite exciting. The basic principle is that the material can transition from amorphous to crystalline state by heating up the material, by passing currents through the material, and through the Joule heating, you heat up the material. If you heat it up beyond the melting temperature, melt it, and then quickly quench it, becomes amorphous. And then if you want to put it from the amorphous state to crystalline state, you heat it up at an intermediate temperature beyond the glass transition temperature, so it will just begin to nucleate around the nucleation site and recrystallize in a polycrystalline state. The polycrystalline state is low resistance, such as shown in here, and the amorphous state is high resistance. It has several orders of magnitude differences in resistance, so you can use it by switching it between the two states and measuring the resistances. So the device structure looks typically like this: a top electrode, a bottom electrode with a what we call a heater, with a small area. So, and you have the phase change material in here. Most of the material will be crystalline, and this region in here, when the current goes from top to the bottom electrode, will crowd around here and create a lot of heat in here. And this region will be programmed repeatedly between amorphous state and crystalline state. Okay, a lot of papers. As you can see, that the number of papers have been going up every year. And so there's a lot of activities in the technical community. Today, the phase change memory is from the technical demonstration side. Mnemonics has shown, or now Micron has shown 1 gigabit phase change memory array using 45 nanometer technology. And if you go out and buy one of the few Samsung cell phones, this is a cell phone taken apart, you can find a 512 megabit phase change memory inside some of these cell phones. So it is in product right now. All right, so energy. Because of the physics, is to have Joule heating, so it goes by if you think about the area of this tiny bottom heater electrode, it goes scale with the area of the heater area, okay, because of the Joule heating. So this is a research current, which is the higher the current you require to melt and quench the device. And these are a bunch of the data. The black circles are the data from the literature, and the red circles are the wishful thinking from the ITRS. And you can see that, of course, because it depends on area, so there's a straight line down here. The current density required is about anywhere from 20 to 40 megaamp per centimeter square. So not milliamp, megaamps per centimeter square. And you doing materials and engineering sometimes could allow you to have another 10x lower of the current density. So that sets the energy dissipation. These devices switch around like 1.5 volts or so. So that you can, and then I will go through some analysis later on. So next device, spin torque transfer memory, STT-RAM. I am no expert on magnetic fields and spins and so on and so forth. So, but here's a paper I found from the ISSCC last year showing this is I believe, 16 kilobit memory array. If you go through the literature, the right current density is about 3 to 5 megaamp per centimeter square for the spin torque transfer memory. So from current density, the spin torque transfer memory also works by current density. So it scales with the device area. So as you scale down, you require it's the same density, but you require a smaller current. Another topic, another device is the metal oxide RM. This one is even harder than the phase change memory. You can see the number of publications kind of explode in the past 5 years or so. What is that? What is RM? It is very simple: top electrode, bottom electrode, and sandwiched in between a metal oxide. And these metal oxide could be very simple, like hafnium oxide, aluminum oxide, the kinds of oxide that we're familiar with in the high-K literature. And the processing is low temperature compatible, so you can imagine building these kinds of things on the back end of the line of a CMOS. There are two modes of operation of these RM. One is what I call the unipolar mode. The other one is bipolar mode. The bipolar mode is easier to understand. So here's current versus voltage. Let's say you start from a high resistance stage, HRS. You'll ramp up the voltage at some point, and it will go through a soft breakdown of the metal oxide. So the current will shoot up at become the low resistance state. And if you don't limit the current by some kind of a compliance, either in your measurement system or by a transistor that is in series with it, then you will actually blow up the device, and you basically have a hard breakdown and you have a short. But if you do limit it to the soft breakdown, then the device will switch into a low resistance state, like this blue curve in here. If you want to go back to the high resistance state, you go to a negative voltage and you will go back to this state. This is a bipolar mode. Another kinds of materials and sets of electrode give you the unipolar mode, in which you can do this kind of programming using one direction of the voltage only. And the physics of which is poorly understood for both of these bipolar mode and unipolar mode. So that's a little bit problematic. But the theory, some of the kind of prevailing theory is that there is a formation of, through the soft breakdown, you create oxygen vacancies as a conductive filament in here, which bridge the two electrodes, and the oxygen will get, the vacancy is formed, and the oxygen gets stored in one of the electrode, for example, in the tinitride electrode. And then when you apply the opposite direction, you push the oxygen back down and disrupt the filament, and therefore you can switch between two states. So this is a prevailing theory, but hardly could be considered as well accepted or well proven. So that's the physics of the RM. And the RM, because it is filamentary conduction, so it doesn't scale with the area. The energy doesn't depends on area, and I'll show you some analysis of the energy later on. Conductive bridge memory, which I'm sure that the next speaker will talk a little bit more, quite a bit more about it, basically is nanoscale electroplating. You have two electrodes in here. You have a electrolyte in which you basically do a electroplating of, let's say, this copper in here. You dissolve the copper in here, and the copper migrate and form filament, and when it touches, it forms a filament, and when it goes the other direction, you dissolve the copper into the electrolyte, and you disrupt the filament. And this is a picture from Vivek Subramaniam in this campus in here showing formation of silver filament in here. You see this silver filament during programming, and here's some modeling showing filament growth. This is kinetic Monte Carlo modeling showing filament growth until it touches. Once it touches, it becomes, goes through a lateral growth. So this is kind of similar to what the RM has. So you have a filament, and then when it touches, the filament grows. So again, this is a filamentary conduction mechanism, so it doesn't scale with the area, but it does have a very interesting relationship, which is a voltage-time relationship, in which the longer you do this, once you touch, the longer you stay in that condition, the filament gets bigger and bigger, so you get lower and lower resistances. But then while you're doing it, you burn more and more energy. Why? Because more current going through once the filament touches themselves. So here are some IV characteristics. So you start from high resistance state. Once and then it start touching, and you could go to the other direction to make it untouched again, disconnected again. You can actually scale it down to an atomic scale. This is a very interesting paper from Tarabe-san showing a platinum and silver sulfide and silver electrode, and you can basically do tiny electrode plating, nanoscale electrode plating, and have one atom touching and not touching, and making this is sort of like the ultimate scale of these kind of devices. All right, so let's talk about energy. Reading a bit of energy of the memory is really determined by the resistance of the lowest resistance state, the LRS. Let's say you have a typical read voltage, or you basically, let's say you have pre-charged bit line, and you have a typical read voltage of 200 millivolts, which is typical. You say you have a read time of 10 nanosecond. The typical resistance ranges, the low resistance states of the resistance ranges for this metal oxide RM and the conductive bridge memory can span many orders of magnitude, because it's a filamentary conduction. For the CBRM, you can grow this filament to be very thick, and you can have very low resistance, or you can have one atom touching it, you have very high resistance in the low resistance state. Similar for the metal oxide, you can have many filaments forming, and therefore your resistance will be very low. Or you could grow the filaments fatter, so it can be very low resistance. So it has spanned a very large range of resistance states. For the STT-RAM and the phase change memory, it's more of a function of the physics of the materials and the way the resistance work. So it's a little bit less range in here. The phase change memory tend to be of the order of kiloohms to megaohms, and the STT-RAM is a few kiloohms. So as you do this math in here, the read energy expands from about 4 attojoule to about 400 attojoule. So depending on the value of the low resistance state. Okay. Now writing the bit depends on the physics and the materials. So you need to split the two discussion in here. Let's talk about write energy for phase change memory and STT-RAM. Both of these works on current density, so they scale to the area. So the write voltage for phase change memory is roughly constant because the physics of the electronic switching, which tends to be about anywhere from 1 to 2 volts. The STT-RAM switches at around half a volt to a volt, so this is the write voltage. The write current density for phase change is about 20 to 40 megaamp per centimeter squared, while STT-RAM is about 3 to 5 megaamp per centimeter squared. The write speed for phase change tends to be of the order of 10 to 30 nanosecond or so. You can have faster or slower ones. And STT-RAM is about 1 to 10 nanosecond or so. So the write energy per bit, and currently, for those devices that we're making, it's obviously scaled with the device size. For phase change, it's about 3 picojoule, and for STT-RAM, it's about 0.3 picojoule per bit. Okay, so that's of course, as you scale down these smaller and smaller, these will go down. For example, we have done some experiment to scale down the area of the bottom electrode quite substantially, and we were able to experimentally measure 0.3 picojoule per bit. Okay, so scaling down is possible. All right, now to write energy for this filamentary conduction like RRAM and CBRAM is a little bit more complicated. There's a lot more nuance to it. Let's start with the write voltage again. The write voltage for RRAM is about 1.5 to 2 volts. So this is RRAM kind of IV curves. This is a CBRAM IV curve. You can see it's about 1 to 2 volts. The CBRAM is about 1.5 to 3 volts. Okay. Now for write current, it's really more or less like a free variable because it really depends on the value of the resistance value of the low resistance state. When you try to write from low resistance state to high resistance state, that's when you burn the most power because your resistance is very low, so the current is very high. The resistance of the RRAM and the CBRAM of these range in here, tens of kiloohms to all the way can be like gigaohm, right? So that range has a very tremendous range, and today, many of the RRAMs are operating at around a microamps of programming current. Some are even lower, like there are some papers that show 10 nanoamps of programming current. And the CBRAMs are operating about tens of microamps or 100 microamps or so. Now, obviously, there's a huge trade-off between lower current and read current and the read current that's available and the retention time, because if you have, let's say you have a write current of a microamp, right? If you don't want to have a read disturbed, then the read current has to be substantially lower than the write current. Otherwise, when you're reading and you write the cell, that's no good, right? So typically, the read current has to be like at least 10x, maybe probably, hopefully 100x smaller than the write current. So if you have a 1 microamps of write current, then your read current has to be like 10 nanoamp. Then that means that it takes a very long time to read the cell. Then the cell will be very slow, right? So that's one trade-off in the read time, okay? And also the other one is the retention. Remember, this is the filamentary conduction. If you have a small write current, that means your filament is rather weak. You're very narrow filament. You're almost not making a connection, so that the retention time will suffer, because if you are almost making a connection, that means you will almost break the connection. Okay, so there's a tremendous trade-off in here. The write speed is interesting also for both of these things. The write time decreases exponentially for the write voltage. So this data, experimental data, showing that the write pulse width versus the write amplitude, the pulse amplitude, is a voltage time relationship. It goes exponentially. So if you increase the voltage, then you would decrease the write time exponentially. So the energy being V squared divided by R of the low resistance state times the time. So if you increase the voltage, then you're increasing the square, but the time goes down exponentially. So if you want to consume low energy, you would use a large voltage amplitude to decrease the time to reduce the energy. Okay, so you do that. Of course, you cannot do that without bound. If you increase the voltage very high, then of course you kill the device, right? So there's some bounds to it. Today, the write energy that you find in the literature for RAM range from 60 femtojoule per bit to about 3 picojoule per bit, depending on the resistance value that the people are targeting. And the CBRAM ranges at around 1 to 5 picojoule per bit. All right, so a lot of people talk about cross-point memory and so on. So there's a bit line and a word line, and there's a memory element, and there's a selection device, which is important. I'm not going to talk about today. We focus more on this. What I want to draw your attention to is the wires. Right? Just like logic, we cannot just talk about logic device without talking more about the wires. So we need to talk about the wires. All right. So this is the resistance per unit length of the wire versus the width of the wire, assuming a unit aspect ratio wire. This is the ITRS expectation. This is the models from wire using these models with and without a barrier, and it looks like this. And you can see that it rises very quickly, and that causes a tremendous problem, because the memory, if you want to build a memory array of a certain array size, then if you have hot wire resistance, you need to drive current through the wire, then you have an IR drop, and pretty soon you don't have enough voltage to write the cell. Right? All right. So here is the computation, and also when you are writing the memory cell in a big array, you are consuming two kinds of energy. One is the charging energy, CV charging energy in the wires in the cross-point array, and the other one is the static energy, basically the energy you consume, the IR joule heating you consume in the resistance of the wire. So we've done some analysis in here, but one of my students did some analysis a few days ago, looking at energy per bit for writing a bit of a array of 1,000 by 1,000 array, and of course it depends on the resistance of the cell itself. So here is the dynamic energy in here. This is CV squared charging energy. This is of the order of 1/10 of a picojoule or so. And these are the green and the blue and the black ones are the energy consumed in the wire for various cases of the on resistance of the memory cell itself. Okay, and these points in here demarcate the point where towards the left of it, these curves are not valid because you have so much IR drop that you cannot write the cell anymore. So the net of that is that the static energy and the dynamic energy are somewhat comparable when you have a low on-state resistance. When you have a higher on-state resistance of the memory cell, then the static energy is not that important. Okay. So final slide in here, and here is this chart showing the energy per switch, basically CV squared for transistors in here, for the smallest transistors, W over L of 1. And this is versus year, so here's the data from IBM, we collected from the literature, data from Intel, we collected from the literature. This is the ITRS expectation. So the write energy per bit for the field devices that I talk about today kind of hovers around here, out of scale, out of chart, somewhere around here. And the write energy for wire are somewhere around here for a 1 kilobit by 1 kilobit array in 1 kilo cells, 1,000 cell by 1,000 cell array in here. And the read energy per bit can range very widely because depending on your low resistance state of your target. Of course, then the next up is to figure out how many logic transitions we're making per memory write or per memory read. Okay. So if I close, I want to thank all my students and postdocs. There are about 5 to 6 students who are working on these memory projects, and our sponsors, and many of the industrial sponsors for our memory technology research initiative that have been helping us with some of the work. And finally, some of the technical collaborators from companies who have been helping us along the way. Thank you.
Thanks, Philip. Do we have time for maybe a couple questions? Any questions in the audience?
Yes, Alan.
In these conductive bridge memories, what's limiting the speed to the nanosecond range? What is fundamentally why it's slow?
Fundamentally, why is it slow?
You can scale the gaps. You don't have to build the bridges. Don't have to be long. What if you just go down to the limiting? What's limiting?
Okay.
Speed.
When you first form that filament, it will take a little longer time. But when you, in subsequent cycle, when you break the filament, you don't need to completely dissolve the entire filament. All you need to do is to create a gap, at least longer than a tunneling gap, and you break the connection, right? So that part could be rather fast. At some point, you will be limited by diffusion of these atoms, and also at some point you will be limited by the electrochemical reaction that goes on. I don't know what that limit is.
One more question.
In the balance in energy cost between switching the memory element versus reading out the memory element, I think you said something about that, but give us some feeling. But what is the overall balance between those two things?
You mean writing versus reading?
Yes, that would be one way of putting it. But the reading, I also include the communications cost.
Yes. Yeah, the reading also you need to bring up charge up the bit line and word line and stuff like that, right? So if you go back to here, all right.
Maybe you can also be realistic. There's also a connector between the CPU and...
Yeah. I haven't considered that yet. I haven't considered that yet. But the wire energy is somewhere around here, and the read energy per bit is somewhere around here. Okay, so the wire energy is somewhere. The read energy per bit could be quite a bit lower than the wire energy consumed by the wire if your target resistance value is rather high. However, there's some trade-off. If your target resistance is high, that means your read speed is going to be slow.
Okay, maybe we should take this discussion offline.
Okay.
All right?
Thank you.
Simply due to time. So let's thank Professor Wang one more time for a very nice talk.